Hello, this is the third section of the 2008 PAT. So this is sort of medium length physics questions. There's probably 3, 4, 5 of them, something like that. So we'll run through these here. Question 23, this problem will consider the possibility of storing electrical energy in capacitors made up of two parallel metal plates, each of area A, separated by thickness D of a dielectric, electrical permittivity P. Right, so they've changed that from our usual epsilon on our permittivities. A capacitor will store a charge Q equals CV. Capacitance is given by this. Okay, they've given us a lot of information here. V is the voltage across the capacitor. Yeah, so capacitance, as we know from our studies of that, is how much charge are we storing per unit potential difference. So that's what we've got in this Q equals CV, just rearrange the definition of capacitance. Given that work done in charging the capacitor is this, show that the work done to charge a parallel plate capacitor is this one. Right, okay, it looks like we're just subbing stuff in. So they've given us this. We've got what C is and we've got what Q is, and they seem to have been removed in here. So Q, we're going to have C squared, V squared. One of those C's is going to cancel. So let's do CV squared over 2. Now we just have to put in what C is, because yeah, V stays there. So C is PA over 2D, and we got the V squared. There we go. So that just comes out exactly as we want. So that was a nice straightforward starter. This work done is equal to the energy stored in the capacitor. In practice, a capacitor is limited by the breakdown voltage of its dielectric. Right. Okay, proportional to the thickness, and then we've got some V max here, BD. Right, where B is a constant that depends on the material. Right, so if you just put too much voltage over it, everything starts falling apart. So determine how the maximum energy stored in a capacitor depends on the mass m of the dielectric, its density D, and other constants. Right, that's quite an interesting collection of things going on here. So we've got this V max then. So that's going to give us a W max based on V max, because W is proportional to V squared. So if we've got a maximum on V, we're going to have a maximum on W. So our maximum W, which is what we're looking for here, this is the maximum energy stored, it's our maximum work done. So that is going to be, where was it? V max is BD. So we've got P A B squared D squared over 2D. Okay, so obviously we can cancel D's top and bottom. And now they're saying we need to, how that depends on the mass and the density. So the density is the mass over volume. So let's write this out then. So we've got D is M over, well, that's volume rather than voltage. So let's actually write it out as volume, mass over volume. And the volume is the area of the plates multiplied by the distance between them, because we've got these two parallel plates separated by some distance. So we end up getting this, A times D thing. So that is M divided by A times D. Right, so this is good. So A times D, A times little d is M over big D, and we've got an A times D here. So we've now got that W max is going to be, so we've got P, we've got a B squared, A times D is M over big D, and we've got that 2 there. Right, is this fitting what they've asked for? So they want it to depend, how it depends on mass, so yeah, and density D, and other constants. So we got 2, we got B is a constant, and we got P is a constant. Right, so that looks fine. I'm happy with that. Right, so now we're on to this last bit then. For a dielectric, they've given us P, they've given us B, they've given us D. Calculate the maximum energy which can be stored. Oh, they've given us M, so they've given us all of the numbers. Right, we just need to type everything in. And then comment on the practicality of using a capacitor of this type to smooth the output of a 1 kilowatt domestic wind turbine in a gusty area, right? So we're going to be working out some maximum energy. We're going to have to compare it to this 1 kilowatt to see if it can do anything that's going to smooth it out. So, right, let's put these numbers in then. So in this case, our W max is, we've got, make a little bit more space, 2 times 10 to the minus 11. Our B is 2 times 10 to the 7. So we're going to have 4 times 10 to the 14 there when we square it. Then we've got our mass of 1. Divide it by 2 times 1000. Okay, so we've got a lot of things. We can cancel on all of this. What have we got? So we've got minus 11 plus 3 minus 3. Wow, that's all just disappeared. And then we've got that cancels with that, which just leaves us with 4 joules. Right, well, that's not very much, particularly if we've got, so if we've got this gusty area here. So what they're saying with that is we're going to have, if you were looking at some, you know, power curve for this wind turbine, then we're going to get these gusts going up. It's going to be quite peaky in various ways, up to this 1,000 joules per second. Well, we're only contributing 4 joules from one of these capacitors. So 1,000 joules per second versus 4 joules. I mean, the 4 joules is just too small. So we'd need a lot more of those capacitors. So we need, in order for this to be in any way effective at smoothing out the these drops in the wind power that we've got going on here. Right, yeah, that was an interesting one. It's another one of those ones where you have to sort of see if you can work out what's going on as you're going along. So it's the only real jump that we had was, how do you bring in this density here of getting that AD in? I mean, if you're not sure and you can't see these things, as soon as they start, you know, giving you this sort of stuff, just start writing out the equations and eventually they drop in. I mean, that's more or less what I was doing there. I couldn't immediately see what I was going to be doing at this step. You know, once we were sitting here, we had this and we needed to turn that into something which was just to do with these constants. But once you start filling in these bits, you know, okay, well, I've got a D and an M. There's got to be something here in this volume which is new. This isn't included in our W max equation that we've got here. We want to keep M and D in, so there must be something to do with this volume, and it's got to be, we need to eliminate everything else that isn't a constant. So looking at what we had in W max, our P and our B were constants. The things that were causing us problems were A and D. So you're piecing these things together in a deductive way of, well, what do we have to get rid of? And it turns out that our 2 problem things, A and D, happen to fit in with our volume. So all of those were interacting with each other, and it just meant they could drop away. So yeah, don't despair if you can't see the immediate path. Just keep on chipping away and try and work at it from both ends. You know, what is it that we need at the bottom, as in we don't want A and D in it? What have we got at the top? We've got an introduction of M and D. How are we going to move from one to the other? So yeah, that's a nice question. I like that one. Let's push on though. Don't want to be whittering on about that for too long. A pilot takes off from an airfield 5 kilometers west of a house. Right, so we've got an airfield here. We've got a house here. We've got 5 kilometers between the two of them. Flies in a direction 60 degrees east of north. So that's going that way. After 5 minutes, she sees that direction to her house is now at an angle of 135 degrees to her course. So you come up here, and then we've got that angle there is going to have to be 135 degrees. How far away is she from the house? Okay, so we've got, well, we know that that's 30 degrees. And that is going to be then 45 degrees because that's a straight line. So we've got sine rule going on here because we want to know what that is, that distance there. So let's do sine rule with the length on the top then, so we can keep it where it is. Sine x over sine 30 degrees is going to be equal to, what was it, 5 over sine 45 degrees. So that's going to be the x divided by a half. So that's yeah, that's 2x. Yeah, so I've done that right, no? Yeah, so 2x is equal to 5 divided by 1 over root 2. So 5 root 2. 5 root 2. So x equals 10 divided by, what am I doing? No, not 10. 5 root 2 over 2. So, yeah, what's the best way of doing this? I suppose I could make that a 10 root 2 over 4. Not really sure what the best way. Well, they've told us to use 1.4 for that. So let's just do that, 7 over 2. I was making heavy work of that. I don't know why I was trying to come up with something more clever. 3.5 kilometers. I suppose I really clocked that we were using that 1.4 for root 2, which makes the sums a little bit quicker. Yeah, that was just straightforward vectors question. So easy 4 marks there. Now here we go, the annoying simultaneous equation question. So forest is inhabited by 3 species of macaw. I'll give a bit more of the space at the top of the page. All of the same shape, different sizes and colours. The food consumption of each type is proportional to the square of the length. Okay. Given that a crimson macaw, so C plus a ruby, put together are twice as long as a scarlet. Okay. Crimson macaw and a scarlet macaw put together eat as much as a ruby macaw, and that was based on square of the length. So C squared plus S squared equals R squared. Okay, so these red ones are greedy parrots. C, 2 crimson macaws and a scarlet macaw are 1 meter. 2 crimson plus a, what was it, a scarlet equals 1 meter. Determine the lengths of the 3 macaws. Right, okay. I mean, these are just so tedious, it's ridiculous. So let's get rid of S first of all then. So we've got S is equal to 1 minus 2C. So that means from there we've got C plus R equals 2 minus 4C. 5C equals 2 minus R. We can stick all of this then into the middle one. So we've got C squared plus 1 minus 2C squared equals, well, R squared, which is 2 minus 5C squared. So let's solve this for C. C squared plus 1 minus 4C plus 4C squared equals 4 plus 25C squared minus 20C. Okay, so C squareds, we've got 20C squareds. C's, we've got minus 16C. And then numbers, we've got what, 4 minus 1 is 3. So are we going to be able to split the middle term here? We need 2 numbers that multiply as 60 and add up the minus 16. Oh, right, okay, so that's good. 20C squared minus 10C minus 6C plus 3 equals 0. 10C multiplied by 2C minus 1. And then we need, so we've got another 2C minus 1. So that's going to have to be a minus 3. Okay, so 10C minus 3 multiplied by 2C minus 1. So we need C equals 0 equals 0. C equals a half or 3 over 10. Right, so if C is a half or 3 over 10, if C was a half, we're getting, the S would be equal to 0. Well, that doesn't look very good, so we can't have that. Else S would be equal to 0. So if we've got C is 30 centimeters, then that means S is going to be 40 centimeters, and R will be equal to, what's our relationship between C and R? Oh, here we go. So 100 and, well, 5 times 0.3, so R will be 50 centimetres, because we've got 2 minus 1.5. Oh, that's it. Okay, so yeah, not much fun, but they seem to do fewer of these nowadays, which is just as well. I mean, there's nothing interesting about these at all. Question 26, is that all right? This is the last one in this set. Graph below shows high tides at Wadebridge, July the 7th, 2008. So this is only 3 marks, so they're not expecting a lot. At what time of day at what time in the morning to the nearest hour, so morning is going to be this bit, is the tide height changing most rapidly? So we want the steepest gradient. So it's going to be about here, isn't it? Which is what, 7 a.m. So 7 a.m. And what is the rate of change in centimeters per minute at this time? Right, so that's in meters. So we're now going centimeters per minute. So we want to try and get, again, I know I always say it, but it's a pain trying to read these things off the screen. Right, let's extend this gradient up to something like that. So we're looking at around about 300 centimeters in, what's that, 2 hours, so 120 minutes. So our centimeters per minute is going to be 2.5. So let's go with that, 2.5 centimeters per minute. Other estimates are available. So yeah, not a bad 3 questions. The first one was certainly the tricky one. Okay, 25 with a parrots was fiddly. The other 2 were really quick, but the first one was quite interesting. I think that means we've only got 1 more question in this paper, the usual old style long question, so that'll be up in the next video.